Well, here it is. Graphics, sound, and input are all finally working on the GameTank, and a prototype platformer ties it all together. This is certainly the most game-like software to run on this system thus far. While there's still much work to be done, I at least feel like I can say I've built a game console. Over the last month, I fixed several issues with the hardware that would have made running games next to impossible. The biggest of these was that graphics were getting scrambled when written to video RAM. You can see here that some of the font data got badly distorted. To figure this out took days of reviewing the schematics, probing with an oscilloscope, and even testing the graphics board with an Arduino instead of the 6502 CPU. The culprit turned out to be gate delays on the write enable signal, causing a change in memory address to arrive at the video RAM chip before the end of the write strobe. Each of the address signals only has to pass through a single gate, a 74HC257 multiplexer, which controls whether the CPU or the DMA engine sets the address seen by VRAM. In contrast, the write strobe has to pass through two of these multiplexers as well as an OR gate. That ends up being a whopping 3 gates. Now, it seems pretty terrible, but just how bad is it? To find out, let's take a closer look at the datasheet for these chips. At 5 volts, the OR gate only has a typical 6 nanosecond propagation delay. This isn't so huge on its own, but the multiplexer adds on a whole 11 nanoseconds for a total delay of 17 nanoseconds. The datasheet for WDC's 65CO2 shows us that the address lines remain stable until shortly after Phi 2, the system clock goes low. If we scroll up, we can see that this address hold time is only 10 nanoseconds. Because our timing skew is bigger than this, bytes written to VRAM would also be written to other addresses as well. Fixing this involved tapping into an unused AND gate, gluing on an inverter, and adding a small maze of bodge wires to shorten the write enable pulse by half. This is still long enough for the write to go through, but now it finishes before the next address is loaded. At long last, all of video RAM is accessible. The next major fix concerns the sound card, specifically the circuit that mixes the outputs of the 4 channels. At least for me, analog electronics is quite a bit more difficult than digital, so some trial and error would be required. On this breadboard, I've broken out the outputs from each channel and arranged a replacement mixer circuit. These capacitors form a high-pass filter and prevent any one channel from overly sinking current from the others. These resistors do nothing. I also had to jam a resistor into this socket because I didn't realize when I ordered the part that it was an open collector output, meaning that I'd have to add my own pull-up resistor. To assist in these analog audio misadventures, I wrote this sound test app that lets me manipulate each of the audio registers live with the gamepad. All the channels have a control byte which selects both volume and octave. The square wave channels each have another byte to select pitch, while the wave channel has a pointer to the start of an audio clip, stored in dedicated wave RAM. Now the current batch of cartridges I'm using have 8 kilobytes of storage. This can make things a little bit tricky because wave RAM holds 4 kilobytes, while a full screen's worth of graphics takes up 16K. Thankfully, Piotr Fusik on GitHub has posted an inflate implementation for the 6502. Including this in my game code means that I can use the zopfly utility to compress files on my PC and extract them to anywhere in RAM on the GameTank. Creating graphics files is relatively straightforward. To convert an image, it must be resized to 128 pixels by 128, flipped upside down, and saved as an indexed color bitmap using a specially crafted palette file. Then, simply remove the bitmap header using your favorite hex editor. To select the header without having to read it, you can check the length of the file. A 128 by 128 pixel image should be hex 4000 bytes. If your file is, say, hex 4438 bytes, then you need only select the first hex 438 bytes and delete them. In HXD, if you set your row width to the same as the image width, you can even sort of see the outline of your image to confirm that you did it correctly. Now, compress the file with zopfly using the --deflate argument, and check the final size using ls. A converted photo isn't ideal for this compression method, so going from 16,384 bytes to 4,360 bytes isn't too shabby. A sprite sheet for a game, having simpler images and repetition, can be compressed even smaller. The inflate routine itself takes up 508 bytes, but that still leaves us a decent amount of space for code, map data, and even some audio samples. Another existing tool that's come in handy is TileKit by RxI. This map editor lets you set rules to procedurally select tiles from your sprite sheet based on different arrangements of shapes. Edges of platforms can automatically use the beveled version of a tile, or platforms of a specific size can be given a special graphic of their own, like these lamps. TileKit can export its map data as JSON, which is pretty easy to write converters for. My conversion approach is to divide the map into chunks of 16 tiles by 16, and save them as separate binary files, which I then reference from my assembly code. Here, I have imported 4 chunks of the map. Let's take a look at how they get used. Prev screen and next screen are run when the player character hits the left or right side of the screen. They increment or decrement a variable called current tile map. Draw tile map refers to current tile map in indirect indexed mode, so incrementing or decrementing current tile map plus 1 moves the pointer 256 bytes in either direction. Let's find out what happens if we head to the leftmost screen and keep going. Nothing too special. Any contiguous 256 byte region can be rendered as a tile map with full collision detection. The first screen we passed is actually the music data. The rest is compressed sprites, animation definitions, and eventually the code for subroutines. Well, I implied that we might eventually reach game code, but it's actually pretty inevitable to get stuck, due to the chaotic nature of these tile maps. Any values 0 through 15 are treated as impassable, and parts of the compressed sprites have a great many zeros. Going off the right side of the screen is not as interesting. This area is all zeros, and as the game is written right now, it's impossible to pass. My next plans for this project are to expand this demo into an adventure game with enemies, locked doors to find key fors, and some kind of goal. I'm also getting ready to revise all of the boards now that the current prototype is a fragile mess of dangling bodge wires. The next version will likely be a stack of only 2 boards and will have a 3D printed case. By the way, the emulator has also progressed quite a bit. With keyboard inputs and sound support added, it's become an invaluable tool for rapid iteration. Eventually, I want to open source and share a kit version of the game system, and want to write up a detailed programming manual to support development for this platform. As always, this has been Clyde Schaefer, and thanks for watching my video. Hope you found it interesting.